The cosmic shadow dance. What is dark matter? Our universe is a vast and mysterious place filled with wonders that boggle the mind and stretch the imagination. It is full of stars, planets, and galaxies, each with their own unique characteristics and mysteries. But what we see is just a small part of what's out there. The observable universe is only a fraction of the entire cosmos. The majority of the universe is made up of something we can't see. This unseen substance makes up about 85% of the total mass of the universe. We call it dark matter. Despite its name, dark matter is not just an absence of light. It is a form of matter that does not interact with electromagnetic forces. Dark matter is like a cosmic ghost. It doesn't emit light, reflect light, or absorb light. This makes it incredibly elusive and difficult to study. This makes it invisible to our telescopes. Traditional methods of observation are useless when it comes to detecting dark matter. We can't see it directly. No matter how powerful our telescopes become, dark matter remains hidden from direct observation. So, how do we know it's there? Scientists have devised ingenious methods to infer its presence. We know dark matter exists because of its gravity. Its gravitational pull affects the motion of galaxies and stars. Gravity is the force that pulls things together in the universe. It governs the motion of planets, stars, and galaxies. Dark matter's gravity affects how stars and galaxies move. Without dark matter, the outer regions of galaxies would fly apart. It's like a cosmic shadow dance, where we see the effects but not the dancer. The invisible hand of dark matter shapes the structure and evolution of the universe. Understanding dark matter is crucial for understanding the true nature of our universe. It holds the key to many cosmic mysteries. Researchers around the world are working tirelessly to unlock the secrets of dark matter. Their discoveries could revolutionize our understanding of the cosmos. Though we have much to learn, each discovery brings us one step closer to unveiling the hidden fabric of the universe. Gravity's whispers, the evidence for dark matter. In the 1930s, astronomer Fritz Zwicky noticed something strange. He was studying galaxies in a cluster. Clusters are groups of galaxies held together by gravity. Zwicky realized that the galaxies were moving too fast. The visible matter in the cluster didn't have enough gravity to hold them together. They should have flown apart. He concluded that there must be some unseen matter providing the extra gravity. This missing mass became known as dark matter. Cosmic speedsters and gravitational lenses, unmasking the invisible. Over the decades, more evidence for dark matter emerged. Astronomers observed stars orbiting galaxies at incredibly high speeds. These speeds were much faster than expected based on the visible matter in the galaxies. Another clue came from gravitational lensing. Massive objects like galaxies can bend the path of light. This is similar to how a magnifying glass bends light. Astronomers observed light from distant galaxies being bent around massive clusters. The amount of bending indicated that there was much more mass present than what we could see. This unseen mass, again, pointed to the existence of dark matter. The cosmic web. Dark matter's role in the universe. Dark matter isn't just scattered randomly throughout the universe, it forms a vast, interconnected structure called the cosmic web. This web is made up of filaments and clumps of dark matter. Galaxies are not scattered randomly either. They are found along the filaments of this cosmic web. Dark matter acts like a scaffold, providing the gravitational glue that holds galaxies and galaxy clusters together. Without dark matter, galaxies would likely not have formed in the early universe. The universe would be a very different place. Section 5. Galaxies in a spin. How dark matter holds things together. Imagine a spinning top. As it spins, the outer edges move faster than the center. Galaxies rotate in a similar way. But here's the mystery. Stars in the outer regions of galaxies are moving much faster than they should be based on the visible matter alone. It's as if something invisible is giving them an extra gravitational kick. That something is dark matter. It forms a halo around galaxies, extending far beyond the visible disk of stars and gas. This halo of dark matter provides the extra gravity needed to keep these speeding stars from flying off into space. Section 6. The missing mass problem, a cosmic accounting error. When astronomers add up all the visible matter in the universe, it's not enough to explain the way things move and interact. There's a significant amount of mass missing from our cosmic inventory. This discrepancy is known as the missing mass problem. Dark matter provides the solution. It accounts for the missing mass, bridging the gap between what we see and what we know must be there. In fact, dark matter makes up about 85% of the total matter in the universe. The familiar atoms that make up stars, planets, and us make up a mere 15%. Section 7. WIMPs, axions, and sterile neutrinos. The hunt for dark matter particles. What exactly is dark matter made of? This question has puzzled scientists for decades, driving them to explore the farthest reaches of the universe and the tiniest particles known to physics. That's one of the biggest mysteries in modern astrophysics. Despite its elusive nature, dark matter is believed to make up about 27% of the universe's mass-energy content. Scientists have proposed several candidates for dark matter particles, each with its own unique properties. These candidates range from the well-studied to the highly speculative. One leading candidate is the WIMP, or weakly interacting massive particle. WIMPs are thought to be heavy and slow-moving, which would make them a perfect fit for dark matter. WIMPs are hypothetical particles that interact very weakly with ordinary matter, making them difficult to detect. Despite this, numerous experiments around the world are dedicated to finding them. Another possibility is the axion, a very light particle that was originally proposed to solve a problem in particle physics. Axions are intriguing because they could explain both dark matter and certain anomalies in quantum chromodynamics. Axions could also be a component of dark matter. If they exist, they would be produced in vast quantities in the early universe and could still be floating around today. Yet another candidate is the sterile neutrino. Unlike regular neutrinos, which are already known to exist, sterile neutrinos are purely theoretical. Neutrinos are tiny, almost massless particles that interact very weakly with matter. They are so elusive that trillions of them pass through us every second without leaving a trace. Sterile neutrinos are hypothetical particles that interact even more weakly than regular neutrinos. If they exist, they could be a significant component of dark matter, adding another piece to the cosmic puzzle. Section 8. Deep underground and in the sky. Searching for dark matter's signature. The hunt for dark matter particles is a challenging endeavor, because these particles interact so weakly with ordinary matter. Detecting them requires extremely sensitive experiments. Some experiments are located deep underground, shielded from cosmic rays and other sources of background noise. These experiments use large detectors to look for the faint signals that might be produced when dark matter particles collide with atoms. Other experiments are looking for indirect evidence of dark matter interactions in space. For example, when dark matter particles annihilate, they might produce gamma rays which could be detected by telescopes. Section 9. A universe more strange than we imagine. Dark matter's implications. The discovery of dark matter has revolutionized our understanding of the universe. It tells us that the familiar matter we see around us is just a small fraction of what's out there. The universe is a much stranger and more wondrous place than we once thought. Dark matter plays a crucial role in the formation and evolution of galaxies and galaxy clusters. It shapes the large-scale structure of the universe, influencing the distribution of galaxies and the cosmic web. Furthermore, understanding dark matter could help us unravel some of the deepest mysteries in physics, such as the nature of gravity and the fundamental building blocks of matter. Section 10. Dark matter versus dark energy. Untangling the cosmic mystery. Dark matter is not to be confused with dark energy. While both are invisible and make up a significant portion of the universe, they are fundamentally different. Dark matter, as we've discussed, interacts gravitationally, pulling things together. Dark energy, on the other hand, acts like a repulsive force, pushing things apart. Observations of distant supernovae have shown that the expansion of the universe is accelerating. This acceleration is attributed to dark energy, which makes up about 70% of the total energy density of the universe. Section 11. Mapping the invisible. Charting the distribution of dark matter. Astronomers are working to map the distribution of dark matter throughout the universe. By studying the motions of galaxies and the bending of light, they can create detailed maps of dark matter concentrations. These maps are helping us understand the structure of the cosmic web and the role of dark matter in galaxy formation. They are also providing valuable clues in the search for dark matter particles. Section 12. The future of the universe. Dark matter's influence. In this section, we delve into the profound impact that dark matter has on the cosmos and how it will shape the destiny of everything we know. The fate of the universe is intimately linked to the nature of dark matter and dark energy. These mysterious components make up the vast majority of the universe's mass energy content, yet they remain largely enigmatic to scientists. The amount of dark matter will determine whether the universe continues to expand forever or eventually collapses in a big crunch. This scenario, where the universe's expansion halts and reverses, could lead to a catastrophic end where all matter is compressed into a singular point. If the density of dark matter is high enough, its gravity could eventually halt the expansion of the universe and cause it to contract. This contraction could lead to a dramatic and violent end, potentially resetting the cosmic clock. However, if the density is too low, the universe will continue to expand indefinitely. This endless expansion would result in a cold, dark, and desolate cosmos, where galaxies drift apart and stars burn out, leaving behind a vast emptiness. The interplay between dark matter and dark energy will also shape the future of the universe. Dark energy, which is driving the accelerated expansion of the universe, competes with the gravitational pull of dark matter. The relative strengths of these forces will determine whether the expansion of the universe continues to accelerate or eventually slows down. If dark energy prevails, the universe could face a big rip, where galaxies, stars, and even atoms are torn apart. Understanding these forces is crucial for predicting the ultimate fate of the cosmos. Section 13. Unraveling the enigma. The quest for dark matter continues. The quest to understand dark matter is one of the most exciting and challenging frontiers in modern science. It is a journey into the unknown, driven by our insatiable curiosity to comprehend the fundamental nature of the universe. New telescopes, experiments, and theoretical models are constantly pushing the boundaries of our knowledge. With each passing year, we are getting closer to unraveling the enigma of dark matter and unlocking the secrets of the invisible universe. The journey is far from over, but the thrill of discovery continues to inspire generations of scientists.